Hello, dear students. You're welcome to Arc Institute. I'm Dr. R.K. Saini. As you know, we are currently studying D and F block element, which is an important topic for IIT-JEE and NEET. If you want to score better in exams, then today's lecture is going to be very important for you. In this session, I will explain metallic bond in D block element and its related properties such as melting point, boiling point, hardness, enthalpy of atomization in a simple and exam-oriented way. These concepts are frequently asked in competitive exams, so make sure you don't miss any part of this lecture. Watch this video till the end to get complete clarity. And don't forget to subscribe the channel for more such powerful lectures. Now, let's start with most important concept, metallic bonding. According to metallic bond, cohesive force between metal atoms, it takes place. Many theories explain metallic bond formation, but most important are electron C model developed by Drude and Lorentz in 1900 century and MOT. According to electron C model or free electron concept, free electron theory or electron C model. Electrostatic force of attraction exists between kernel and mobile electron. In d block element, less energy difference between ns and n-1d electron. Both electrons take part in bonding and hence are known as valence electron. After removal of valence electron, the remaining part of atom is known as kernel. And as kernel is positively charged ion. And the mobile electrons are valence electron. When electrostatic force of attraction becomes stronger between kernel and mobile electron, then strong metallic bond between metal atoms, or we can say strong cohesive force. These are the mobile electron present in lattice, and the positively charged ion are known as kernel. For a strong metallic bond, more stronger electrostatic force of attraction is there. Therefore, kernel should be smaller in size. Kernel should be smaller in size. It carry high charge, and if diffuse orbitals present in the kernel, then strong electrostatic force of attraction are there between kernel and mobile electron. You know about diffuse orbital? These are the orbitals which have irregular lobes in their space. Therefore, their screening effect or shielding effect is very poor, and hence strong electrostatic force of attraction exists between kernel and mobile electron. This model is most important to explain metallic bond strength down the group, because 3D and 4D series 3D and 4D series size is sufficiently greater for 4D element, but the size of 4D and 5D element are almost equal due to F contraction, or it is the effect of length and height contraction. Therefore, the metallic bond strength mainly depends upon the diffuse nature of d orbital. You know that 3D, 4D and 5D are diffuse orbital, and when d orbital far away from the nucleus, then increases diffuse nature. And when diffuse nature of orbitals are there, their poor shielding effect or imperfect shielding, strong electrostatic force of attraction exists between kernel and mobile electron. And this model explains cohesive force between metal in metallic bond. Another theory is MOT, which used to explain metallic bond strength mainly across the series. According to MOT, molecular orbital theory, when number of unpaired electron increase per atom, then they make a strong metallic bond. The number of unpaired electron either in ground state or in excited state of ns and n-1d, both orbitals take part in bonding, then stronger metallic bond is there, because when more number of unpaired electrons are there, then these electrons enter into BMO, bonding molecular orbitals, and when pairing of d electrons takes place, then electron enter into high energy, or we can say enter into anti-bonding molecular orbitals, and they have higher energy, therefore metallic bond become weaken. And hence when we go across the series, then number of unpaired electron per atom increases from left to right. For example, in case of scandium, number of unpaired electron is 1. But when during the bond formation, ns electron transfer into, or we can say 4s electron transfer into 3d, and hence 3 unpaired electrons are present during the bond formation in scandium. Similarly, bond formation similarly in case of titanium, ns electron are also enter into 3d. ns 4s electrons are also enter into 3d, and they become unpaired. They become unpaired means 4 unpaired electrons are there, vanadium and chromium, and hence the number of unpaired electrons are increases across the series up to middle element, and then number of unpaired electron decreases after manganese, because d electrons are paired. For example, in case of iron, 3d6, and hence paired electrons are there, and ns electron are excited or promote into np. 4s enter into 4p during the bond formation, they become unpaired, and the 4p has higher energy state, therefore they make weak metallic bond than n-1d or 3d electron. It means the metallic bond strength increase across the series up to middle element, and then metallic bond become weaker. And in last element, like a zinc, cadmium and mercury, no unpaired electrons are there, and their kernel formation is very difficult. Their kernel formation is very difficult because they have highest ionization enthalpy in their series, and hence they possess weak metallic bond. And this is the order of metallic bond, and the following properties, mainly melting point, boiling point, hardness and atomization enthalpy, are depends upon the metallic bond strength. However, these properties are also depends on other factors like as types of crystalline structure. In previous lecture we find they mainly possess BCC, body centered cubic structure, CCP, cubic closed packing structure, HCP, hexagonal closed pack structure. The packing efficiency in BCC is 68%, and in CCP and SCP packing efficiency is 74%. The coordination number of BCC in element is 8, but the coordination number of CCP and HCP is 12, and as these factors are also important to determine sublimation enthalpy or atomization enthalpy, melting point, boiling point, as well as hardness of the element. But in general, these factors are mainly depends upon the metallic bond strength, and we know that the metallic bond become stronger across the series up to middle element, and then it become weaker, and hence these properties or these values are increased up to middle element and then decrease. However, manganese and technetium group number 7 have half filled electronic configuration, and we know that the stable electronic configuration of element have less tendency to bond formation, like as inert gas. The inert gas have fulfilled electronic configuration, means more stable, therefore their bond formation tendency is very less, lacking the chemical bond formation tendency. Similarly, manganese and technetium are also have less metallic bond properties, and hence these properties increases up to chromium, generally chromium, and then decreases. For example, heat of atomization is also known as sublimation enthalpy. For example, in case of scandium, heat of atomization is a enthalpy or heat change during the formation of 1 mole of gaseous atom, gaseous isolated atom from metal, and hence it is known as atomization enthalpy or also known as sublimation enthalpy. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. See the atomization enthalpy in kilojoule per mole. Atomization enthalpy of scandium is 327 kilojoule. In case of titanium, 473 kilojoule per mole. In case of vanadium, highest atomization enthalpy and highest melting point of vanadium in 3D series, 515 and 515 kilojoule per mole. This value given in your NCERT, but in JD the value is 562 kilojoule per mole. In chromium, the atomization enthalpy is 397. In manganese, the atomization enthalpy is only 286 kilojoule per mole. In iron, atomization enthalpy 464. In cobalt, 425 kilojoule. Nickel, 436 kilojoule. In copper, 339 kilojoule per mole. And in zinc, notice in zinc, the atomization enthalpy is only 126 kilojoule per mole because it possesses weakest metallic bond in their series due to very difficult to formation of their kernel. What do you mean by kernel? After removal of valence electron, the remaining part of the atom is known as kernel, and the element which has higher ionization enthalpy, then their kernel formation is very difficult. Means it possesses very weak metallic bond and no unpaired electron is there. Therefore, weakest metallic bond present in the zinc, and hence its atomization enthalpy or sublimation enthalpy is lowest. After zinc, the manganese has lowest atomization enthalpy in 3D series. Notice the point, the vanadium has highest atomization enthalpy or sublimation enthalpy, and after that titanium occupies second position in 3D series. As we discuss metallic bond strength or electron C model, metallic bond strength increase down the group. For example, 3D metallic bond are 4D element are stronger than 3D and 5D element are stronger than 4D. But the metallic bond of 6D element is also weaker because the size of 6D element are much larger than 5D, and as 5D element make strongest metallic bond. These properties, atomization enthalpy, also increase down the group. In case of group number 6, chromium, next molybdenum, 4D element, and in 5D element is tungsten. Tungsten is hardest metal, possess highest metallic bond, strongest metallic bond, and have highest melting point among all known metals, and its atomization enthalpy is also highest among all known metals. It means metallic bond strength increase down the group. However, the metallic bond strength decrease down the group in last group of D block element, means in group number 4. Reason is similar. The size of cadmium is sufficiently larger than zinc, means their kernel and mobile electron have less electrostatic force of attraction, and due to highest ionization enthalpy of mercury in D block element, its kernel formation is very difficult and hence possess weakest metallic bond, or we can say these elements are soft metal, not a hard. However, except group number 14, 12, these D block elements are very hard because cohesive force is non-directional interaction between metal atom, and hence it is stronger. However, D block element, namely zinc, cadmium, and mercury, are soft metal, or you know that mercury is a liquid at room temperature. Their melting point, boiling point are hard and are known as volatile metal, and other D block element have less volatile nature. Next, we discuss melting point. Melting point also depends upon the metallic bond strength as well as crystalline structure, sublimation enthalpy, etc. The metallic bond also increase across the series and then up to middle element and then decrease. However, the highest melting point is also in case of chromium and vanadium. The melting point of scandium is nearly 15 100 degrees centigrade. Titanium is also greater, nearly 1600 degrees centigrade. The melting point of vanadium is 1900 degrees centigrade, and in chromium is nearly equal, 1875 degrees centigrade. And then the melting point of manganese is suddenly dropped, only 1240 degrees centigrade. Iron is also greater than 50 and is nearly 1500. Cobalt is nearly and roughly decreases, slightly decrease, nearly 495. Nickel slightly decrease, 440, and copper also decrease, 180. And the melting point of zinc is lowest in their series, only 420 degrees centigrade. Therefore, vanadium and titanium in 3D, among 3D, vanadium and titanium. Vanadium is highest melting point. Chromium is second most element which possess highest melting point, or roughly we can say melting point of chromium and vanadium is nearly equal. These are the point of melting point, atomization enthalpy, hardness. Hardness is also increased across the series. Titanium and vanadium are very hard element, and then molybdenum and then tungsten. Okay. Thank you.